Okay, so in looking back at the coin tossed experiment, to get to the binomial distributions, you want to look above the VARs menu. You'll see a little word that says distribution on it. So if I hit second distribution, it pulls up a lot of choices. These are things we'll eventually get to. We're looking for binomial at this point. And so you just keep scrolling down until you see binomial PDF and CDF. We want binomial, let's see, for exactly 2 heads, we want binomial PDF. And it's going to ask us for some information. So we are tossing 3 coins. That's our trials. The probability of success is 0.5. And the which of those 3, which one am I actually interested in? That'd be 2. And then hit enter. And so that's what it should look like on the main screen for you. And then just hit, there you go, 0.375. Let me scroll down to the gauge problem. Okay, let me go back to that distribution menu again. All right, binomial, let's see. So if we want exactly, in this first one, we wanted exactly 1. Trying to get too far off the screen here. Okay, so there were 4 trials. The probability of success in this case was 0.1, and I want exactly 1 as far as, what's the probability of just 1 occurrence. And so I type that in. That's what it should look like on the home screen. And we should get the same number we got before. More than 1. Okay, so now we're switching from a PDF to a CDF. So we're looking at a range. Now, this one is, well, let's just type it in and we'll kind of talk about what we think it's trying to tell us. So there are still 4 trials. P-value is still 0.1. So we're going to take a guess and see what useful information it gives us. If I want more than 1, right? Well, what happens if I put 1 in? What would happen? And we get 0.9477. Okay, so what the 0.9477 is, that's when we figured out whether it was 0 or 1, right? Probability of it being 0 or 1. We want more than that, so we want to do 1 minus this. And that'll give us the probability of it being just more than 1. Okay, so we have to kind of stop and think about it. I did a CDF up till 1, and what did the calculator do? It calculated up till 0 and 1. Let me see if I can kind of map this out a little bit better for us here. Okay, so what's going on here? So I went back in and I calculated the probabilities of each of the various x values. So I did a PDF to figure out what the probability of that particular value is. Let me kind of clarify in context. So the likelihood of 0 problems is 65%. The likelihood of all 4 of them being broke at the same time is 0.0001. The likelihood that 2 of them are broken, 0.0486. So about 5% of the time, I would walk in and find 2 broken gauges. Okay, so what a binomial CDF does, what a CDF does is it measures things in terms of less than. So in other words, it asked me more than 1. I don't have the ability to type in, hey, start at 1 and go all the way up to 4. I have to think about it in terms of less than. So more than 1 is anything less than 1 I want to subtract. So when it said for more than 1, what I did is I took 0 and 1, took those numbers, added them up, and then I subtracted from 1. It doesn't give us the ability to add up 2, 3, and 4 with that one function. So we kind of have to stop and translate the CDF function in terms of less than. So we'll kind of get some practice on that here in a moment. Okay, so new problem. A genetic trait of one family manifests itself in 25% of the offspring. If 8 offspring are randomly selected, find the probability that the trait will appear in exactly 3 of them. Okay, so let's first clarify, we're talking PDF or CDF here. And since we're looking at exactly 3, now we're talking a PDF. So we're going to go to our distribution menu, and we're going to look for Binomial PDF. And wow, I got all sorts of things. Let me clear this out here. Try that again. Okay, so from PDF, we have 8 trials. The likelihood of success we're saying is 0.25. So we're looking at how many of them have the trait. And I want to know exactly 3 of them. So then I just hit enter from there. And that's what it looks like from the main screen. And so about 20.7% of the time, or about 21% of the time, I would find 3 children that have this particular genetic trait. Okay, well, what about at least 5? Okay, so a little thought experiment before we go to the calculator. I have 0, 1, 2, 3, 4, 5, 6, 7, 8 children, the 8 children that could have this genetic trait in them. If I want at least 5, which of these numbers do I actually want to include? I want at least 5. Well, 5 would be good, 6 would be okay, 7 would be okay, and 8 would be okay. Any of those numbers would be fine. But remember, our CDF function measures things in terms of less than. Okay, so and it do I want 5 included in there, or do I want 4 included in there? What do I want to do with that? Let's kind of think about that for a second. Okay, and so what we're going to do is, since the CDF only gives us less than, I want 4 or less. That'll tell me that piece, and then I want to subtract that from 1 so I can get 5 or more. So let's kind of see how that would look. So go to my distributions and go to Binomial CDF. Okay, there are 8 trials. Probability of success is 0.25. And remember, it does it in terms of less than. So I want 4 or less. Then hit enter. Okay, so what this 0.97 represents, that means if 25% of the children have this, I would find 4 or fewer children that have this particular trait 97% of the time. So to find the 5 or more, I would 1 minus that 0.97, which is 0.027, or about 3%. So I'd expect in about 3% of the cases, so about 3% of the time, I would be able to find 5 children or 6 children or 7 or 8 children that have this particular genetic trait. Okay. In a certain county, 30% of the voters are Republican. If 10 voters are selected at random, find the probability that no more than 6 of them will be Republicans. Okay, so we're talking about a CDF again, and we want to kind of think about, when we say no more than 6, well, what numbers are going to satisfy that if it's no more than 6? So could I have 1 and we'd be okay? Yeah, no more than 6. So if I say you can only invite so many of these people to this party and I want no more than 6 of them to show up, well, 1 could show up and you won't yell at me, or 2 could, or 3 could, all the way up to 6. I don't want any more than 6 included. Okay, in which case I want less than 6, anything 6 and then less than. So when I do the CDF, I can include just the 6, and that'll give me the probability up to that particular number. Okay, so number of trials would be 10. Probability of success is 0.3. And then I want 6. And this will give me anything 6 and less will count. and the probability of success there is 0.989. Okay, now let's switch the question then. What if we switch it to like this? What is the probability that at least 7 are not Republicans? Okay, so we got two issues we got to address. What do they mean by at least? And then how does this not Republican thing, how does that switch our information? Well, the not Republican statement switched our successes. If we define success as being Republican, now we're saying success is not Republican. Well, if Republican is 30%, not Republican would be 70%. So it switches our probabilities of success to 0.7, and then at least 7. So let me kind of go back and spell this out here. Okay, so at least 7 are not Republicans. So what number are we counting up till? So is this, like if I said 5, would that be okay? Or is that 9? Is that okay? So what are we looking, above 7 or below 7? So at least 7 would mean it's got to be 7, 8, 9, or 10. Okay, so when I calculate the binomial CDF of this, then I want up to 6, and I want 1 minus. Okay, so let me go back to our binomial distribution, binomial CDF. Okay, so because they are switching our success from Republican to not Republican, that switches to 0.7. I want up till 6, so that part's going to stay the same. But remember, this is up till 6. I want to know 7 and beyond. So once I get this number, then I want to subtract that from 1. And that 0.649, that physically represents the likelihood of me finding at least 7 that are not Republican, given this description that they did about switching it from 30% to 70%. Okay, the last thing to address with binomial distributions is how do we find the mean and standard deviation of given various parameters of the problem? Well, the mean formula is simply n times p, whereas the standard deviation is the square root of np times a 1 minus p. Now I like to call 1 minus pq, but so quickly it's square root of npq. But let's take a look at an example of this in action. Going back to our Republican question. So in a certain county, 30% of the voters are Republican. How many Republicans would we expect out of 10 random selected voters? And then what's the standard deviation for this distribution? Okay, so in this particular question then, we need to know n, so how many total individuals are in our sample, or how large is our sample. And so in the question, 10 randomly selected voters, 10 represents our n. And then p, of course, represents the probability of success. Since we're looking at the percent of people who are voters, we're defining Republican as success. And so if 30% is the probability of that, then we just need 10 times 0.3. So 10 times 0.3 is, of course, 3. So I would expect 10 people, 3 of them to end up being Republican. Same question or same concept when we look at standard deviation. So we want the square root of 10 times the 0.3 times 1 minus 0.3, which is that one, of course, is just 7. Alright, so that's 3 times 0.7. Okay, so we get square root of 2.1. We actually type that in the calculator. And then if I take the square root of that, I get 1.45, approximately 1.45.